Okay, so now we're gonna do Hamming code. So Hamming code is also quite simple, a bit more complicated, but simple nonetheless, once you get the steps in. So in this case, we have a communication system and it cannot have any mistakes. And it should be able to detect, it should be able to detect two errors on one of hexadecimal messages are just the size of 1. So that means it can be 1 or 2 or F or A in that case. It just has one Einstellung, like one slot in a sense. We read the exercise, it says, gegeben sei ein nicht werktolerantes Kommunikationssystem, welches in der Lage ist, einstellige Codeworte in hexadecimaler Darstellung zu übertragen. Es soll nun dahingehend erweitert werden, dass es mittels eines Hamming-Codes Zweifachfehler erkennen oder das Einfachfehler korrigieren kann. That's the important part. The important part is this guy, and the hexadecimale Darstellung. So in this case, we're going to start off with A. And they're asking us what Hamming distance do we need to be able to fix this issue. This one's pretty simple. We know our formula, the HD minimum to find would be equal to D plus 1. In this case, we want to find two Zweifachfehler erkennen, so it's going to be 2 plus 1, and this is going to be 3, and this is 3 bits. To fix, it's another story. We have to do, again, HD min, and then 2D plus 1, which in this case is going to be 2, and we just want to fix 1, so it's going to be 3 bits. We're done with A. Now B. How many bits, wie viele Bits werden nun jeweils benötigt, um die Informationen und die Paritätsbits nach Hamming zu codieren? Wie lang wird das gesamte übertragende Codewort? It's pretty simple. What we do is, we know that we have a hexadecimal value, right? Hexadecimal values always have 4 bits. For example, if we have F, which is 15, this would be represented in binary as so. So this means we have 4 bits for hexadecimal numbers. So we can say hex is equal to 4 bits, right? All good. And now we want to find basically how many paritätsbits we need. This is pretty easy. We can say that our message is just hexadecimal value. So message will be equal to 4. And now K, which is the amount of parity bits we need, is equal to 1 plus LD of M, or rather, LD of 4. This is going to be equal to 3 bits. And you put in your calculator. Remember that LD is log 2 of M. So remember that. Now that we have that, we can say, okay, what's the actual word we're going to send? It's going to be our hexadecimal plus the parity bits. That means this is going to be 4 bits plus 3 bits. So our actual length is 7 bits for a word. And that's pretty much the solution for it, right? Let me just do here and then add this in my favorites, as I always use it. What the heck? Okay, it's not working. Let's restart the app real quick. It's being a bit weird lately. Okay, whatever. So it's gonna be 7 bits, right? Now let's go with C. C is a bit more complicated, but it's not difficult. In this case, we're just gonna focus on the parity bits. So the parity bits, parity bits are going to play a big part over here. So we can do just here, just a big line. Maybe just write again. So parity bits, beats are 3 bits. So what we're going to do is we're going to do truth table according to how many bits we have. So in this case, we have 3 bits. So we're going to make a truth table like so. Right? Make it a bit bigger here. So 0, 0, 0, 0, 0, 1, 0, 0, 0, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. That's pretty much our whole parity bit, well, so to say, truth table. Now what you want to do is you're going to find in each row, identify where you have only a 1, 1. So meaning you have 1, 1 here. The next would be here. And the next one is here. Once you have that, that's all good. And that's where you're going to write your epsilon or your y's. So let's write our y's here. Oops. So y1, y2, y3. So we're going to erase this now. And the rest of the slots we're going to just fill with x's. x3, x4. And then when we have zeros, we just say that nothing happens. Now what you're going to do is we're going to focus first on y1. And you're going to focus on the column of y1. So you're going to say, take this guy. So we have 1, 1 here. And you're going to just write every single one that you have on this column. So here, here, and here. So we can say that y1 is like relative or is dependent on x1, x2, and x4. Why? Because this is where the ones are. So we have 1, 1, and x1, and x2, and x4. Now we're done with that. We're going to go to the next one. It's going to be the y2. And again, 1, 2, 3. We can say that y2 is equivalent, but relative to x1, x3, then x4. x3, x4, yeah. And this is pretty much it. Now we can go for the next one. Next one will be y3, 1, 1, 1 again. So we're going to have x2, x3, and x4. And we're done with that. Once we're done with that, we will now be able to create our Hamming code table. How you do that is really simple. You're going to start off with writing your x's, so x4, x3, x2, x1, and you're going to do a simple truth table. So in this case, it's going to be quite a long one. It's 3, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Then 1, 2, 3, 4, 3, 4. We copy this once. Good. We're going to do 0, 0, 1, 1. Right? So 0, 0, 1, 1. And then this guy. And then now at the end, 0, 1, 0, 1. Right? Quite simple. And there we go. We have our truth table for our x's, and this is where the y's come in. So the y's are going to be as following. Here, we're going to focus for y3, for example. We start with y3 first, so y3, y2, y1. We're going to start with y3, and y3 focuses on what? It focuses on x2, x3, and x4. Meaning, we're going to do a highlighter for that, those those little columns that we need. So x2, x3, and x4. So we can say this is the whole thing. This is the whole chimichanga that we need. So we do fill, and this is what we need. So basically, once we have this, we want to do an XOR function between these columns. So in this case, it's going to be 0, and XOR means that whenever we have a pair of ones, it'll be 0. If we have a non-pair amount of ones, then it's going to be 1. And if we just have zeros, it's zeros. So you'll see. So 0, 0, the next one is 0, 0. Over here we have 1, 1, which is an uneven amount of numbers. Over here, 1, so it'll be, again, because it's uneven, 1 is just the amount of ones that we have is uneven. Here again, 1, 1. Over here we have 2 1s, so that means it's an even number. So we're going to have 0, and then 0, then 1, 1, and then we have 0 again here, 0, 0, 0, and 1, 1. Although we have 3, it's an uneven number, so an odd number. So yeah, that's pretty much it. The next thing we're going to do is going to be x1, x1, x3, and x4. So x1, x3, and x4. So basically this, guys. And we're going to do the same business. So 0, 1, 0, 1. Then it's going to be 1. It's going to be 0, 1, 0, 1, 0, 1, 0, 0, 1, 0, 1. Now that we have that, that's all perfect. Now we're going to do the last one, which is going to be y1. So y1 has to focus on what? x1, x2. So we can just expand this, and then it's going to be x4. So it's the same situation that we have here. 0, then there's going to be 1, there's going to be 1, there's going to be 0, 0, 1, 1, 0, 1, 0, there's going to be 0, there's going to be 1, there's going to be 1, 0, 0, and 1. It's a bit confusing to do this kind of big numbers and such, but once you get the hang of it, you can just start off. So you just gotta focus and not make a lot of mistakes, and yeah. Now we can delete this, and we can actually make our table look nice now. Make an official table. This is my favorite part. Just make it just big now. So that's our table we have. So we're done with the Algebra C in a sense. Now we want to see if the message we get on D. So we're gonna copy this table. Let's copy it. We're gonna go down and we're gonna put it here. Now we want to see the messages we get. Now in these messages, we know that our message is 7 bits long. We already proved this. So we're gonna separate every number by 7. So this is 7, this is 7, this is 7, this is 7, this is 7. And from there, we know that we have 4 bits or 4 numbers for a hexadecimal value and 3 numbers for parity bits. What does that mean is, then first number on the right, which is 0, this guy over here, we're going to separate it again. So we have 4 bits for the hexadecimal value, 3 bits for the parity bits. Same thing here. 0, 100, 1001, then 100, then 1, 1, 1, 0, and then 1, 1, 1, 1, 1, 1, 1, 0, 100. So what we want to do here is we want to find the mistakes. How do we do this? Well, the first step you want to do is take this and find this number in our table. So we're going to find it. So 0, 0, 0, 1, 0, 1. Let me see, 0, 1, 0. Here it is, 0, 1, 0, 1. However, we have 2 errors. It's not the same. The parity bit we get here is not the same as the one we have over here, right? So how do we know whether we have an error in our parity bits or our actual message? This is quite easy. We just have to remember. And just bring it up here. Give me a second. Because I have it written on my computer here. Okay, if we have 2 errors, meaning 2 errors in our parity bits, it means we have an error in our message. I will write this in the script as well, in the cheat sheet, because it's important. If we have 1 error, then we only have an error in the parity. So in this case, if we look at the 0, 1, 0, 1, and we look at this 0, 1, 0, 1, and we have and we compare this guy with this guy, we can see that we have an error of 2. So there's an error in our message, meaning our parity is correct, meaning we have to find a parity which is 0, 0, 0, which is this guy, and see the actual message. And as you guys can see, the only mistake differentiating this one and this one will be the 0 here. So the fixed message would look like as follows. Let me just move this little guy over here, maybe. Let's go back here. This is going to look like 0, 1, 1, 1, and then 0, 0, 0. So now we can see that when we go to 0, 1, 1, 1, 0, 1, 1, 1, and 0, 0, 0, they're the same. So that's our fixed error. We already fixed it now. Let's go with the next one again. The next one has 0, 100. So let's find 0, 100. And then we have 1, 1, 0, 1, 1, and then we have 100 here. Meaning the difference is just this guy and this guy. Meaning we have an error in our parity. Meaning this actual message is correct. So now we do it the other way around. We find the 0, 100. So 0, 100 in this case is this guy, and the parity, the right parity bit is 1, 1, 0 rather than 100. So we're going to write that. 0, 100, and 1, 1, 0. That's our right message. Now we're going to do the next one, which is 1001 or 1001. And 100, as you guys can see, it's correct. It's the same thing as here. So this one is correct. Now we're going to do the next one, 1110 and 1111, which in this case, we're going to try to find the 1110. And we find it here. And as you guys can see, we have 2 errors differentiating our parity bits, meaning the message is erroneous. The parity bit is correct. So the parity bit, we have this parity bit, for example, meaning that we only have an error, a mistake in the last digit, which is this guy. Sorry, this guy. I'm just confusing the numbers now. So in this case, we can write that our number is basically like that. Now we're going to do the same thing over here. 1110 and 100. So 1110 and 100 is this guy. And as you guys can see, it's the same thing. So it's correct. So that's pretty much the whole exercise done. And yeah, I think that's pretty much it for Hamming when it comes to Hamming. So yeah, that's it.